Coordination compounds. Introduction. Werner's theory of coordination compounds. Alfred Werner, in 1866 to 1990, a Swiss chemist, was the first to formulate his ideas about the structures of coordination compounds. He studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of a primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl2, or PdCl2 have primary valence of 3, 2, and 2 respectively. In a series of compounds of cobalt-3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate solution in cold, but some remained in solution. 1 mole CoCl3 into 6NH3 yellow gave 3 mole AgCl. 1 mole CoCl3 into 5NH3 purple gave 2 mole AgCl. 1 mole CoCl3 into 4NH3 green gave 1 mole AgCl. 1 mole CoCl3 into 4NH3 violet gave 1 mole AgCl. These observations, together with the results of conductivity measurements in solution, can be explained if 1. 6 groups in all, either chloride ions or ammonia molecules or both, remain bonded to the cobalt ion during the reaction, and 2. The compounds are formulated as shown in table, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valence are 6. Table. Formulation of cobalt-3 chloride ammonia complexes. Color. Formula. Solution conductivity corresponds to yellow CONH3 3 plus 3Cl minus 1:3 electrolyte. Purple COCl NH3 5 2 plus 2Cl minus 1:2 electrolyte. Green COCl2 NH3 4 plus Cl minus 1:1 electrolyte. Violet COCl2 NH3 4 plus Cl minus 1:1 electrolyte. Two compounds have identical empirical formula COCl3 into 4NH3 but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are 1. In coordination compounds, metals show two types of linkages, that is, valences, primary and secondary. 2. The primary valences are normally ionizable and are satisfied by negative ions. 3. The secondary valences are non-ionizable. These are satisfied by neutral molecules or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. 4. The ions or group bound by the secondary linkages to the metal have characteristic spatial arrangements corresponding to different coordination numbers. In modern formulations, such spatial arrangements are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square bracket are called counter ions. He further postulated that octahedral, tetrahedral, and square planar geometrical shapes are more common in coordination compounds of transition metals. Thus, CONH3 3 plus, COCl NH3 5 2 plus, and COCl2 NH3 4 plus are octahedral entities, while NiCO4 and PtCl4 2 minus are tetrahedral and square planar, respectively. Example 1. On the basis of the following observations made with aqueous solutions, assign secondary valences to metals in the following compounds. Formula. Moles of AgCl precipitated per mole of the compounds with excess AgNO3. 1. PdCl2 into 4NH3, 2, 2, NiCl2 6H2O, 2, 3, PtCl4 2HCl, 0, 4, COCl3 4NH3, 1, 5, PtCl2 2NH3, 0. Solution: 1. Secondary 4, 2. Secondary 6, 3. Secondary 6, 4. Secondary 6, 5. Secondary 4. Difference between a double salt and a complex. Both double salts as well as complexes are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salts such as carnallite, KCl MgCl2 6H2O, more salt, FeSO4, NH4 twice SO4 6H2O, potash alum, KAl SO4 twice 12H2O, etc. dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 4- of K4FeCN6 do not dissociate into Fe2+ and Cn- ions. Definitions of some important terms pertaining to coordination compounds. A. Coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. For example, COCl3 NH3 is a coordination entity in which the cobalt ion is surrounded by 3 ammonia molecules and 3 chloride ions. Other examples are NiCO4, PtCl2 NH3 twice, FeCN6 4-, CONH3 6 3+. B. Central atom or ion. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bound in a definite geometrical arrangement around it is called the central atom or ion. For example, the central atom or ion in the coordination entities NiCl2 H2O4, COCl NH3 5 2+ and FeCN6 3- are Ni2+, CO3+, and Fe3+, respectively. These central atoms or ions are also referred to as Lewis acids. C. Ligands. The ions or molecules bound to the central atom or ion in the coordination entity are called ligands. These may be simple ions such as Cl-. Small molecules such as H2O or NH3, larger molecules such as H2NCH2CH2 NH2 or NCH2CH2 NH2 3, or even macromolecules such as proteins. When a ligand is bound to a metal ion through a single donor atom, as with Cl-, H2O or NH3, the ligand is said to be unidentate. When a ligand can bind through two donor atoms as in H2N CH2CH2 NH2, that is ethane 1,2-diamine, or C2O4 2-, that is oxalate, the ligand is said to be identate. And when several donor atoms are present in a single ligand as in NCH2CH2 NH2 3, the ligand is said to be polydentate. Ethylene diamine tetraacetate ion, that is EDTA4-, is an important hexadentate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydentate ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidentate ligands. Ligand which has 2 different donor atoms and either of the 2 ligates in the complex is called ambidentate ligand. Examples of such ligands are the NO2- and SCN- ions. NO2- ion can coordinate either through nitrogen or through oxygen to a central metal atom or ion. Similarly, SCN- ion can coordinate through the sulfur or nitrogen atom. D. Coordination number. The coordination number, that is Cn, of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ions PtCl6 2- and NiNH3 4 2+, the coordination number of Pt and Ni are 6 and 4 respectively. Similarly, in the complex ions, that is FeC2O4 3 and COEN3 3+, the coordination number of both Fe and CO is 6 because C2O4 2 and En, that is ethane 1,2-diamine, are didentate ligands. It is important to note here that coordination number of the central atom or ion is determined only by the number of sigma bonds formed by the ligand with the central atom or ion. Pi bonds, if formed between the ligand and the central atom or ion, are not counted for this purpose. E. Coordination sphere. The central atom or ion and the ligands attached to it are enclosed in square bracket and is collectively termed as the coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. For example, in the complex K4FeCN6, the coordination sphere is FeCN6 4- and the counter ion is K+. F. Coordination polyhedron. The spatial arrangement of the ligand atoms which are directly attached to the central atom or ion defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar and tetrahedral. For example, CONH3 6 3+ is octahedral, NiCO4 is tetrahedral, and PtCl4 2- is square planar. Figure shows the shapes of different coordination polyhedra. G. Oxidation number of central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pairs that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses following the name of the coordination entity. For example, oxidation number of copper in CuCN4 3- is +1 and it is written as Cu1. H. Homoleptic and heteroleptic complexes. Complexes in which a metal is bounded to only one kind of donor groups, for example, CONH36 3+, are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor groups, for example, CONH34Cl2+, are known as heteroleptic. Nomenclature of coordination compounds. Nomenclature is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names, particularly when dealing with isomers. The formulas and names adopted for coordination entities are based on the recommendations of the International Union of Pure and Applied Chemistry, that is IUPAC. Formulas of mononuclear coordination entities. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in a concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formulas. 1. The central atom is listed first. 2. The ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. 3. Polydentate ligands are also listed alphabetically. In case of abbreviated ligand, the first letter of the abbreviation is used to determine the position of the ligand in the alphabetical order. 4. The formula for the entire coordination entity, whether charged or not, is enclosed in square brackets. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligand abbreviations are also enclosed in parentheses. 5. There should be no space between the ligands and the metal within a coordination sphere. 6. When the formula of a charged coordination entity is to be written without that of the counter ion, the charge is indicated outside the square brackets as a right superscript with the number before the sign. For example, COCN6 3 minus, CrH2O6 3 plus, etc. 7. The charge of the cations is balanced by the charge of the anions. Naming of mononuclear coordination compounds. The names of coordination compounds are derived by following the principles of additive nomenclature. Thus, the groups that surround the central atom must be identified in the name. They are listed as prefixes to the name of the central atom along with any appropriate multipliers. The following rules are used when naming coordination compounds. 1. The cation is named first in both positively and negatively charged coordination entities. 2. The ligands are named in an alphabetical order before the name of the central atom or ion. That is, this procedure is reversed from writing formula. 3. Names of the anionic ligands and in -0. Those of neutral and cationic ligands are the same except aqua for H2O, amine for NH3, carbonyl for CO, and nitrosyl for NO. While writing the formula of coordination entity, these are enclosed in brackets. 4. Prefixes mono, di, tri, etc. are used to indicate the number of the individual ligands in the coordination entity. When the names of the ligands include a numerical prefix, then the terms bis, tris, tetrakis are used. The ligand to which they refer being placed in parentheses. For example, NiCl2PPH3 twice is named as dichloridobase, that is triphenylphosphine, nickel 2. 5. Oxidation state of the metal in cation, anion, or neutral coordination entity is indicated by Roman numeral in parentheses. 6. If the complex ion is a cation, the metal is named as the same element. For example, CO in a complex cation is called cobalt and Pt is called platinum. If the complex ion is an anion, the name of the metal ends with the suffix -ate. For example, CO in a complex anion, CO SCN4 2- is called cobaltate. For some metals, the Latin names are used in the complex anions. For example, ferrate for Fe. 7. The neutral complex molecule is named similar to that of the complex cation. The following examples illustrate the nomenclature for coordination compounds. 1. CrNH3 3 H2O3 Cl3 is named as triamine triaquachromium 3 chloride. Explanation. The complex ion is inside the square bracket, which is a cation. The amine ligands are named before the aqua ligands according to alphabetical order. Since there are 3 chloride ions in the compound, the charge on the complex ion must be 3+, that is, since the compound is electrically neutral. From the charge on the complex ion and the charge on the ligands, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecules. Therefore, the oxidation number of chromium must be the same as the charge of the complex ion, +3, 2, CO, H2N CH2 CH2 NH2 3, 2, SO4 3 is named as triethane 1,2-diamine cobalt 3 sulfate. Explanation. The sulfate is the counter anion in this molecule, since it takes the 3 sulfates to bond with 2 complex cations. The charge on each complex cation must be plus 3. Further, ethane 1,2-diamine is a neutral molecule, so the oxidation number of cobalt in the complex ion must be plus 3. Remember that you never have to indicate the number of cations and anions in the name of an ionic compound. 3. AgNH3 twice, AgCN twice is named as diamine silver 1, dicyanidoarengantate 1. Example 2. Write the formulas for the following coordination compounds. A. Tetraamine aquachlorido-cobalt 3 chloride. B. Potassium tetrahydroxidozincate 2. C. Potassium trioxalato-aluminate 3. D. Dichlorido-bis, that is ethane 1,2-diamine cobalt 3. E. Tetracarbonyl nickel 0. Solution: A. CONH3 4H2O Cl Cl2. B. K2ZnOH4. C. K3AlC2O4 3. D. COCl2En2 plus. E. NiCO4. Example 3. Write the IUPAC names of the following coordination compounds. A. PTNH3 twice ClNO2. B. K3CrC2O4 3. C. COCl2En2 Cl. D. CONH3 5 CO3 Cl. E. HgCOSCN 4. Solution: diamine chlorido N platinum 2. B. Potassium trioxalatochromate 3. C. Dichloridobis ethane 1,2-diamine cobalt 3 chloride. D. Pentaamine carbonato cobalt 3 chloride. E. Mercury 1 tetrathiokineto S cobaltate 3. Isomerism in coordination compounds. Isomers are two or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. Two principal types of isomerism are known among coordination compounds, each of which can be further subdivided. A. Stereoisomerism. 1. Geometrical isomerism. 2. Optical isomerism. B. Structural isomerism. 1. Linkage isomerism. 2. Coordination isomerism. 3. Ionization isomerism. 4. Solvate isomerism. Stereoisomerisms have the same chemical formula and chemical bonds, but they have different spatial arrangement. Structural isomerisms have different bonds. A detailed account of these isomers are given below. Geometric isomerism. This type of isomerism arises in heteroleptic complexes due to different possible geometric arrangements of the ligands. Important examples of this behavior are found with coordination numbers 4 and 6. In a square planar complex of formula, that is mx2l2, that is X and L are unidentate. The two ligands X may be arranged adjacent to each other in a cis isomer or opposite to each other in a trans isomer as depicted in figure. Other square planar complex of the type MABXL, that is where A, B, X, L are unidentates, shows 3 isomers, 2 cis and 1 trans. You may attempt to draw these structures. Such isomerism is not possible for a tetrahedral geometry, but similar behavior is possible in octahedral complexes of formula, that is MX2L4, in which the two ligands X may be oriented cis or trans to each other. This type of isomerism also arises when didentate ligands L bond L, for example NH2CH2CH2NH2En, are present in complexes of formula MX2 L bond L 2. Another type of geometrical isomerism occurs in octahedral coordination entities of the type Ma3B3 like CONH33, NO23. If three donor atoms of the same ligands occupy adjacent positions at the corners of an octahedral face, we have the facial, that is FAC isomer. When the positions are around the meridian of the octahedron, we get the meridional, that is MER isomer. Example 4. Why is geometrical isomerism not possible in tetrahedral complexes having two different types of unidentate ligands coordinated with the central metal ion? Solution: tetrahedral complexes do not show geometrical isomerism because the relative positions of the unidentate ligands attached to the central metal atom are the same with respect to each other. Optical isomerism. Optical isomers are mirror images that cannot be superimposed on one another. These are called as enantiomers. The molecules or ions that cannot be superimposed are called chiral. The two forms are called dextro, that is D, and levo, that is L, depending upon the direction they rotate the plane of polarized light in a polarimeter, that is D rotates to the right, L to the left. Optical isomerism is common in octahedral complexes involving didentate ligands. In a coordination entity of the type PtCl2En twice 2+, only the cis isomer shows optical activity. Example 5. Draw structures of geometrical isomers of FeNH3 twice CN4 minus. Solution. Example 6. Out of the following two coordination entities, which is chiral, optically active? A. Cis CrCl2OX twice 3 minus. B. Trans CrCl2OX twice 3 minus. Solution. The two entities are represented as A. Cis CrCl2OX twice 3 minus. B. Trans CrCl2OX twice 3 minus. Out of the two, A. Cis CrCl2OX twice 3 minus is chiral optically active. Linkage isomerism. Linkage isomerism arises in a coordination compound containing ambidentate ligand. A simple example is provided by complexes containing the thiokinase ligand NCS-, which may bind through the nitrogen to give MNCS or through sulfur to give MSCN. Jorgensen discovered such behavior in the complex CONH3,5NO2 Cl2, which is obtained as the red form, in which the nitrate ligand is bound through oxygen, that is -ONO, and as the yellow form, in which the nitrate ligand is bound through nitrogen -NO2. Coordination isomerism. This type of isomerism arises from the interchange of ligands between cationic and anionic entities of different metal ions present in a complex. An example is provided by CONH36 CrCN6, in which the NH3 ligands are bound to CO3+ and the Cn- ligands to Cr3+. In its coordination isomer CrNH36 COCN6, the NH3 ligands are bound to Cr3+ and the Cn- ligands to CO3+. Ionization isomerism. This form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand which can then become the counter ion. An example is provided by the ionization isomers CONH3,5SO4Br and CONH3,5Br-SO4. Solvate isomerism. This form of isomerism is known as hydrate isomerism in case where water is involved as a solvent. This is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. An example is provided by the aqua complex CrH2O6 Cl3 violet, and its solvent isomer CrH2O5 Cl Cl2 H2O gray-green. Bonding in coordination compounds. Werner was the first to describe the bonding features in coordination compounds, but his theory could not answer basic questions like 1. Why only certain elements possess the remarkable property of forming coordination compounds? 2. Why the bonds in coordination compounds have directional properties? 3. Why coordination compounds have characteristic magnetic and optical properties? Many approaches have been put forth to explain the nature of bonding in coordination compounds, viz. Valence bond theory (VBT), crystal field theory (CFT), ligand field theory (LFT), and molecular orbital theory (MOT). We shall focus our attention on elementary treatment of application of VBT and CFT to coordination compounds. Valence bond theory. According to this theory, the metal atom or ion under the influence of ligands can use its n-1d, ns, np or ns, np, nd orbitals for hybridization to yield a set of equivalent orbitals of definite geometry such as octahedral, tetrahedral, square planar, and so on. These hybridized orbitals are allowed to overlap with ligand orbitals that can donate electron pairs for bonding. This is illustrated by the following examples. Table: number of orbitals and types of hybridizations. Coordination number, type of hybridization, distribution of hybrid orbitals in space. 4. sp3 tetrahedral. 4. dsp2 square planar. 5. sp3d trigonal bipyramidal. 6. sp3d2 octahedral. 6. d2sp3 octahedral. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of the valence bond theory. In the dimagnetic octahedral complex CONH36 3+, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d6. The hybridization scheme is as shown in diagram. 6 pairs of electrons, one from each NH3 molecule, occupy the 6 hybrid orbitals. Thus, the complex has octahedral geometry and is diamagnetic because of the absence of unpaired electron. In the formation of this complex, since the inner d orbital, that is 3d, is used in hybridization, the complex CONH36 3+ is called an inner orbital or low spin or spin paired complex. The paramagnetic octahedral complex COF6 3- uses outer orbital, that is 4d, in hybridization, that is sp3d2. It is thus called outer orbital or high spin or spin free complex. Thus, in tetrahedral complexes, 1s and 3p orbitals are hybridized to form 4 equivalent orbitals oriented tetrahedrally. This is illustrated below for NiCl4 2-. Here, nickel is in +2 oxidation state and the ion has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Each Cl- ion donates a pair of electrons. The compound is paramagnetic since it contains 2 unpaired electrons. Similarly, NiCO4 has tetrahedral geometry but is diamagnetic since nickel is in 0 oxidation state and contains no unpaired electron. In the square planar complexes, the hybridization involved is dsp2. An example is NiCN4 2-. Here, nickel is in +2 oxidation state and has the electronic configuration 3d8. The hybridization scheme is as shown in diagram. Each of the hybridized orbitals receives a pair of electrons from a cyanide ion. The compound is diamagnetic as evident from the absence of unpaired electron. It is important to note that the hybrid orbitals do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. Magnetic properties of coordination compounds. The magnetic moment of coordination compounds can be measured by the magnetic susceptibility experiments. The results can be used to obtain information about the number of unpaired electrons and hence structures adopted by metal complexes. A critical study of the magnetic data of coordination compounds of metals of the first transition series reveals some complications. For metal ions with up to 3 electrons in the d orbitals like Ti3+, D1, V3+, D2, Cr3+, D3, two vacant d orbitals are available for octahedral hybridization with 4s and 4p orbitals. The magnetic behavior of these free ions and their coordination entities is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available, that is, as a consequence of Hund's rule. Thus, for D4, that is Cr2 plus Mn3 plus D5 Mn2 plus Fe3 minus D6 Fe2 plus CO3 plus cases, a vacant pair of d orbitals results only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. The magnetic data agree with maximum spin pairing in many cases, especially with coordination compounds containing d6 ions. However, with species containing d4 and d5 ions, there are complications. MnCN6 3- has magnetic moment of 2 unpaired electrons, while MnCl6 3- has a paramagnetic moment of 4 unpaired electrons. FeCN6 3- has magnetic moment of a single unpaired electron, while FeF6 3- has paramagnetic moment of 5 unpaired electrons. COF6 3- is paramagnetic with 4 unpaired electrons, while COC2O4 3- is diamagnetic. This apparent anomaly is explained by valence bond theory in terms of formation of inner orbital and outer orbital coordination entities. MnCN6 3-, FeCN6 3- and COC2O4 3- are inner orbital complexes involving D2sp3 hybridization. The former two complexes are paramagnetic and the latter diamagnetic. On the other hand, MnCl6 3-, FeF6 3- and COF6 3- are outer orbital complexes involving sp3d2 hybridization and are paramagnetic corresponding to 4, 5 and 4 unpaired electrons. Example 7. The spin-only magnetic moment of MnBr4 2- is 5.9 bm. Predict the geometry of the complex ion. Solution. Since the coordination number of Mn2 plus ion in the complex ion is 4, it will be either tetrahedral, that is sp3 hybridization, or square planar, that is dsp2 hybridization. But the fact that the magnetic moment of the complex ion is 5.9 bm, it should be tetrahedral in shape rather than square planar because of the presence of 5 unpaired electrons in the d orbitals. Limitations of valence bond theory. While the VB theory, to a larger extent, explains the formation, structures, and magnetic behavior of coordination compounds, it suffers from the following shortcomings. 1. It involves a number of assumptions. 2. It does not give quantitative interpretation of magnetic data. 3. It does not explain the color exhibited by coordination compounds. 4. It does not give a quantitative interpretation of the thermodynamic or kinetic stabilities of coordination compounds. 5. It does not make exact predictions regarding the tetrahedral and Square planar structures of 4 coordinate complexes. 6. It does not distinguish between weak and strong ligands. Crystal field theory. The crystal field theory, that is CFT, is an electrostatic model which considers the metal-ligand bond to be ionic, arising purely from electrostatic interactions between the metal ion and the ligand. Ligands are treated as point charges in case of anions or point dipoles in case of neutral molecules. The 5d orbitals in an isolated gaseous metal atom or ion have same energy. For example, they are degenerate. This degeneracy is maintained if a spherically symmetrical field of negative charges surrounds the metal atom or ion. However, when this negative field is due to ligands, that is, either anions or the negative ends of dipolar molecules like NH3 and H2O, in a complex, it becomes asymmetrical and the degeneracy of the d orbitals is lifted. It results in splitting of the d orbitals. The pattern of splitting depends upon the nature of the crystal field. Let us explain this splitting in different crystal fields. A. Crystal field splitting in octahedral coordination entities. In an octahedral coordination entity with 6 ligands surrounding the metal atom or ion, there will be repulsion between the electrons in metal d orbitals and the electrons, that is, or negative charges of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand than when it is away from the ligand. Thus, the dx square minus y square and dz square orbitals which point towards the axis along the direction of the ligand will experience more repulsion and will be raised in energy. And the dxy, dyz and dxz orbitals which are directed between the axes will be lowered in energy relative to the average energy in the spherical crystal field. Thus, the degeneracy of the d orbitals has been removed due to ligand electron-metal electron repulsions in the octahedral complex to yield 3 orbitals of lower energy, T2G set, and 2 orbitals of higher energy, EG set. This splitting of the degenerate levels due to the presence of ligands in a definite geometry is termed as crystal field splitting, and the energy separation is denoted by delta 0. That is, the subscript 0 is for octahedral figure. Thus, the energy of the 2 EG orbitals will increase by 3 by 5 delta 0 and that of the 3 T2G will decrease by 2 by 5 delta 0. The crystal field splitting delta 0 depends upon the field produced by the ligand and charge on the metal ion. Some ligands are able to produce strong fields, in which case the splitting will be large, whereas others produce weak fields and consequently result in small splitting of d orbitals. In general, ligands can be arranged in a series in the order of increasing field strength as given below. I minus is less than Br minus is less than SCN minus is less than Cl minus is less than S2 minus is less than F minus is less than OH minus is less than C2O4 2 minus is less than H2O is less than NCS minus is less than EDTF4 minus is less than NH3 is less than En is less than Cn minus is less than CO. Such a series is termed as spectrochemical series. It is an experimentally determined series based on the absorption of light by complexes with different ligands. Let us assign electrons in the d orbitals of metal ion in octahedral coordination entities. Obviously, the single d electron occupies one of the lower energy T2G orbitals in d2 and d3 coordination entities. The d electrons occupy the T2G orbitals singly in accordance with the Hund's rule. For d4 ions, two possible patterns of electron distribution arise. 1. The fourth electron could either enter the T2G level and pair with an exciting electron, or 2. It could avoid paying the price of the pairing energy by occupying the EG level. Which of these possibilities occurs depends on the relative magnitude of the crystal field splitting, delta 0, and the pairing energy P, that is, P presents the energy required for electron pairing in a single orbital. The two options are: 1. If delta 0 is less than P, the fourth electron enters one of the EG orbitals, giving the configuration T2G3 EG1. Ligands for which delta 0 is less than P are known as weak field ligands and form high spin complexes. 2. If delta 0 is greater than P, it becomes more energetically favorable for the fourth electron to occupy a T2G orbital with configuration T2G4 EG1. Ligands which produce this effect are known as strong field ligands and form low spin complexes. Calculations show that D4 to D7 coordination entities are more stable for strong field as compared to weak field cases. B. Crystal field splitting in tetrahedral coordination entities. In tetrahedral coordination entity formation, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. For the same metal, the same ligands and metal ligand distances, it can be shown that delta T is equal to 4 by 9 delta 0. Consequently, the orbital splitting energies are not sufficiently large for forcing pairing, and therefore low spin configurations are rarely observed. The G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since tetrahedral complexes lack symmetry, G subscript is not used with energy levels. Color in coordination compounds. In the previous unit, we learned that one of the most distinctive properties of transition metal complexes is their wide range of colors. This means that some of the visible spectrum is being removed from white light as it passes through the sample, so the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. If green light is absorbed by the complex, it appears red. Table gives the relationship of the different wavelength absorbed and the color absorbed. Table: relationship between the wavelength of light absorbed and the color observed in some coordination entity. Wavelength of light absorbed, that is nanometer. Color of light absorbed. Color of coordination entity. COCl NH3 2+, 535, yellow, violet. CO NH3 H2O 3+, 500, blue-green, red. CO NH3 3+, 475, blue, yellow-orange. COCN6 3-, 310, ultraviolet, pale yellow. CuH2O4 2+, 600, red, blue. TiH2O6 3+, 498, blue-green, violet. The color in the coordination compounds can be readily explained in terms of the crystal field theory. Consider, for example, the complex TiH2O6 3+, which is violet in color. This is an octahedral complex where the single electron Ti3+ is a 3D1 system. In the metal d orbital is in the T2G level in the ground state of the complex. The next higher state available for the electron is the empty EG level. If light corresponding to the energy of blue-green region is absorbed by the complex, it would excite the electron from T2G level to the EG level. That is, T2G1 EG0 gives T2G0 EG1. Consequently, the complex appears violet in color. The crystal field theory attributes the color of the coordination compounds to DD transition of the electron. It is important to note that in the absence of ligand, crystal field splitting does not occur and hence the substance is colorless. For example, Removal of water from TiH2O6 Cl3 on heating renders it colorless. Similarly, anhydrous CuSO4 is white, but CuSO4 5H2O is blue in color. The influence of the ligand on the color of a complex may be illustrated by considering the NiH2O6 2+ complex, which forms when nickel 2 chloride is dissolved in water. If the didentate ligand ethane 1,2-diamine En is progressively added in the molar ratios En is to Ni 1:1, 2:1, 3:1, the following series of reactions and their associated color changes occur. NiH2O6 2+ aqueous green plus En aqueous is equal to NiH2O4 En 2+ aqueous pale blue plus H2O. NiH2O4 En 2+ aqueous plus En aqueous gives NiH2O twice En twice 2+ blue or purple aqueous plus H2O. NiH2O twice En twice 2+ aqueous plus En aqueous is equal to NiEn3 2+ aqueous violet plus 2H2O. This sequence is shown in figure. Limitations of crystal field theory. The crystal field model is successful in explaining the formation, structures, color, and magnetic properties of coordination compounds to a large extent. However, from the assumptions that ligands are point charges, it follows that anionic ligands should exert the greatest splitting effect. The anionic ligands actually are found at the low end of the spectrochemical series. Further, it does not take into account the covalent character of bonding between the ligand and the central atom. These are some of the weaknesses of CFT, which are explained by ligand field theory, that is LFT, and molecular orbital theory, which are beyond the scope of the present study. Bonding in metal carbonyls. The homoleptic carbonyls, that is, compounds containing carbonyl ligands only, are formed by most of the transition metals. These carbonyls have simple, well-defined structures. Tetracarbonyl nickel 0 is tetrahedral. Pentacarbonyl iron 0 is trigonal bipyramidal, while hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of two square pyramidal MnCO5 units joined by a Mn-Mn bond. Octacarbonyl dicobalt 0 has a CO-CO bond breach by two CO groups. The metal-carbon bond in metal carbonyls possess both sigma and pi character. The MC sigma bond is formed by donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. The MC pi bond is formed by the donation of a pair of electrons from a filled d orbital of metal into the vacant anti-bonding pi star orbital of carbon monoxide. The metal to ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. Importance and applications of coordination compounds. The coordination compounds are of great importance. These compounds are widely present in the mineral, plant, and animal worlds and are known to play many important functions in the area of analytical chemistry, metallurgy, biological systems, industry, and medicine. These are described below. Coordination compounds find use in many qualitative and quantitative chemical analysis. The familiar color reactions given by metal ions with a number of ligands, that is, especially chelating ligands, as a result of formation of coordination entities, form the basis for their detection and estimation by classical and instrumental methods of analysis. Examples of such reagents include EDTA, DMG, that is, dimethylglyoxime, alpha-nitroso-beta-naphthol, capron, etc. Hardness of water is estimated by simple titration with Na2-EDTA. The Ca2+ and Mg2+ ions form stable complexes with EDTA. The selective estimation of these ions can be done due to difference in the stability constants of calcium and magnesium complexes. Some important extraction processes of metals, like those of silver and gold, make use of complex formation. Gold, for example, combines with cyanide in the presence of oxygen and water to form the coordination entity AuCN twice minus. In aqueous solution, gold can be separated in metallic form from this solution by the addition of zinc. Similarly, purification of metals can be achieved through formation and subsequent decomposition of their coordination compounds. For example, impure nickel is converted to NiCO4, which is decomposed to yield pure nickel. Coordination compounds are of great importance in biological systems. The pigment responsible for photosynthesis, chlorophyll, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood, which acts as oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the anti-pernicious anemia factor, is a coordination compound of cobalt. Among the other compounds of biological importance with coordinated metal ions are the enzymes like carboxypeptidase A and carbonic anhydrase, that is, catalysts of biological systems. Coordination compounds are used as catalysts for many industrial processes. Examples include rhodium complex, PH3P3, RHCl. A Wilkinson catalyst is used for the hydrogenation of alkanes. Particles can be electroplated with silver and gold much more smoothly and evenly from solutions of the complexes AgCN2- and AuCN2- than from a solution of simple metal ions. In black and white photography, the developed film is fixed by washing with hyposolution, which dissolves the undecomposed AgBr to form a complex ion AgSO2O3 twice 3-. There is growing interest in the use of chelate therapy in medicinal chemistry. An example is the treatment of problems caused by the presence of metals in toxic proportions in plant or animal systems. Thus, excess of copper and iron are removed by the chelating ligands dipenicyllamine and desferrioxime B via the formation of coordination compounds. EDTA is used in the treatment of lead poisoning. Some coordination compounds of platinum effectively inhibit the growth of tumors. Examples are cisplatin and related compounds.